Hi, dear students. Welcome to this session of the question paper discussion of JEE 2021 session 1. And today we will be discussing the question paper of the afternoon session of January 27th. So please listen to the discussion very carefully and try to understand as much details as possible. Okay, let us start. The first question, which structure of protein remains intact after coagulation of egg white on boiling? Now, during coagulation, it's a process of denaturation, in fact, and the primary structure of protein, that is the structure which represents how the building units, namely the alpha amino acids, are joined to one another. So that structure, that is a primary structure, remains intact. It doesn't undergo any change, whereas the secondary, tertiary, and quaternary structures are actually spoiled. So the answer to the question is primary, option B. Option B is the answer. Option B is the answer. Okay, very simple question. And the next question is from inorganic chemistry. You are given 4 ions, MnO4 minus ion where the manganese has +7 oxidation state, and BrO3 minus where the bromine has +5 oxidation state, and SO4 minus where sulfur has +4 oxidation state, and N3 minus where the nitrogen has the -3 oxidation state, which is the lowest oxidation state for nitrogen. So what happens is, in the case of nitrogen, N3 minus, this lowest oxidation state cannot be reduced further. Okay? That means N3 minus ion cannot function as a, it cannot be reduced, and therefore it cannot function as an oxidizing agent. Whereas the other ions with oxidation numbers +7, it may be reduced from +7 to plus possibilities there, +5 to +3 is there, +4 to +2 is there. So there are possibilities of the change in oxidation number from these values to lower values during reactions. But in the case of N3 minus, already the oxidation state is lowest, -3. So further reduction is not possible, and therefore N3 minus cannot function as a reducing agent. Cannot function as an oxidizing agent. That's the question. Okay, so the answer is D. The correct answer is D. Coming to question 3, identify from the following species in which D2sp3 hybridization is shown by the central atom. Now BRF5, you might have studied BRF5, taking the electronic configuration of bromine. It is the d electrons of the outermost shell of bromine being excited, and you have the D2sp3 hybridization in the case of BRF5. And for PtCl2 minus, platinum 2+ ion, platinum, the atomic number is 78. So platinum 2+ ion has a 5d8 configuration, 5d8 configuration. And since the Cl minus is a somewhat strong ligand, the electrons, namely the 8 electrons, will pair up in the d orbitals like this, so that one d orbital is made vacant, and these together with the s and the 3p orbital, 2p orbital can undergo the dsp2 hybridization. So it is dsp2 hybridization in the case of PtCl2 minus to form a square planar complex, whereas in SF6 it is again the D2sp3 hybridization, whereas for CONH3 6 times 3 plus, the cobalt with atomic number 27 and the cobalt 3+ ion with 24 electrons, the configuration will be 3d6 4s2 configuration, and the arrangement of the electrons in the 3d orbitals, the paired state like this, so that 2d orbitals are made vacant, and you can have the hybridization involving the inner d orbitals, that is d2sp3 hybridization, isn't it? d2sp3 hybridization, and so CONS3 6 times 3 plus has the d2sp3 hybridization. SF6, remember, the outer d orbitals are used, so it is not d2sp3, it is sp3 d2 hybridization. And also for BRFI, it is outer d orbitals of bromine being utilized, so it is sp3 d2 hybridization. So remember, while designating the hybridization, it is very important whether it is the inner d orbital or the outer d orbital that is involved in hybridization. So remember, it is sp3d2 for BRFI, it is dsp2, the inner d orbital, for PTCl for 2 minus, and for SF6 it is again sp3d2, the outer d orbital. The d orbital involved is just the outer d orbital only, so it is sp3d2. Whereas for CuNS3 6 times 3 plus, the cobalt 3 plus ion, the d6 configuration, you have the electrons getting paired in the 3 d orbitals, because ammonia is somewhat strong ligand, and the 2 d orbitals are made vacant, and therefore it is inner d orbitals participating in hybridization. So it is d2sp3 hybridization, and that's a question, which is the case in which d2sp3 hybridization takes place. So naturally it is the answer D. D is the one in which d2sp3 hybridization takes place. Okay? And question number 4 is from the basic organic chemistry. You have the contributing structures or the resonance structures, and 1, 2, 3 are given. Look at the structures. In structure 1, of course, there is a double bond and there is a carbonyl group, and there are no charge separation. So that is a neutral resonance structure of the molecule. This compound is what you call CH2 double bond CHCHO is acraldehyde. The compound is acraldehyde. Acraldehyde. And this compound has the neutral resonance structure indicated by 1, which is pretty stable. Neutral resonance structure is pretty stable, remember that. And the structures 2 and 3 are the structures in which there is charge separation. And we find that in structure 2, the oxygen atom is having a negative charge and the carbon atom is having a positive charge. So obviously, this is a favorable charge distribution with the electronegative atom acquiring negative charge. So the charged structure, this one, has a stability, though as not as stable as structure 1, will have some stability because of the negative charge on the electronegative oxygen atom. Whereas in structure 3, what you find is that the oxygen is having a positive charge, which is an unfavorable charge distribution, and therefore represents a structure which is not as stable as 2. So of the 3 structures, the neutral structure 1 is the most stable, and of the remaining 2 structures, 2 is comparatively more stable, so 3 is the least stable. Therefore, the order of stability is 1 greater than 2 greater than 3, isn't it? 1 greater than 2 greater than 3. That is order of stability, and that is the option B in the question paper. Now coming to question number 5, this again in basic chemistry, a question from basic chemistry, or is equally discussed in connection with the introduction of the chapter solutions in physical chemistry. You know, the concentration terms, you have molality, mass percentage, molarity and mole fraction. And you know the definitions. Molality is the number of moles of the solute present per kilogram of solvent. So a term which is expressed only in terms of masses. And mass percentage, again, the mass of the solute in so many grams of the solvent. So that is again a mass-based relationship. Whereas C, molarity, is the number of moles per liter of solution. That means a concentration term where the solute is expressed in terms of the number of moles, whereas the solution is expressed in terms of volume in liters. Okay? And we know that the volume will change with the temperature, and therefore molarity will change with the temperature. So, of course, the last one is mole fraction, which has no unit. It is the ratio of the number of moles of the component to the total number of moles. And therefore, among the four, the one which is dependent on temperature or which will change with temperature is molarity. Molarity is temperature dependent. And you may also remember that normality is temperature dependent. Normality is temperature dependent. So concentration terms where there is a volume involved will obviously change with temperature. Those in which you have only masses expressed will not change with temperature. Okay? Coming to the next question, it's a question from organic chemistry. Of course, it is a three-step conversion. In fact, of course, there are 4 steps given, 1, 2, 3, 4. And the compound is what he calls styrene. It's an aromatic unsaturated hydrocarbon. So this compound, PHCH double bond CH2, that is the styrene, this compound, unsaturated compound. The first is the reaction with the BH3, that is borane. Of course, the monomeric form of diborane. Actually, it must be B2H6, diborane, and the monomeric form is BH3, okay? And in the next step, it is oxidation by an oxidizing agent, hydrogen peroxide in the presence of alkali. Alkaline hydrolysis, oxidation in alkaline medium. And these two reactions together, most of you may be knowing, is what is called the hydroboration oxidation. Isn't it? Hydroboration oxidation. And what is the importance of hydroboration oxidation? These two reactions together, what we call hydroboration oxidation, will do a hydration of the alkene. Hydration of the alkene against the Markovnikov rule. So it is anti-Markovnikov addition. The reaction is both stereoselective and regioselective, you know. It is anti-Markovnikov hydration. And if it is anti-Markovnikov hydration, pH, CH, double bond CH2, in hydration, the H is going to that carbon of the double bond which has less number of hydrogen atoms. So it will be CH2, CH2OH. So this is a compound formed in the first two step together, what you call the hydroboration oxidation reaction. That is anti-Markovnikov hydration. So the product is pH, CH2, CH2OH. Okay? And now there is a reaction with the hydrogen bromide. And the hydrogen bromide is a substitution reaction where the OH is replaced by bromine. So you will have CH2Br. And the fourth step is the reaction with the magnesium in either medium. When you get the Grignard reagent, that is pH, CH2, CH2, MgBr, you get the Grignard reagent, okay? And this Grignard reagent is reacted upon with formaldehyde, and you know the addition of Grignard reagent to formaldehyde, a nucleophilic addition to the carbonyl group of formaldehyde, and the product formed is pH, CH2, CH2, okay, CH2, OMgBr. So that is a product formed. And on hydrolysis by H3O plus, the product obtained will be pH, CH2, CH2, CH2OH. That is option A. It's a good question because you have to know at least 3 reactions or even 4 reactions. Hydroboration oxidation, 1 reaction. Then reaction of the alcohol with HBr, replacement of OH by Br. And then the formation of the Grignard reagent, the magnesium in either medium, and then the reaction with formaldehyde, followed by hydrolysis. Remember that The Grignard reagent reacts with the formaldehyde to give a primary alcohol. It is nucleophilic addition of the Grignard reagent to the carbonyl group of the formaldehyde, and the product is pH, CH2, CH2, and again a CH2, OMGBr, which on hydrolysis gives pH, CH2, 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 OH. Okay, so good question. Now coming to the next question, it is pretty simple. We are given 4 processes and some connectivities are there with the substances used in that reaction or in the process, and you are asked to identify the incorrect pair. Wacker process, you may be remembering it is, one simple example is say ethylene with oxygen, H2O. The catalyst is PdCl2 in presence of some CuCl2, and the product formed is CH3CHO. A method of preparing aldehydes, carbonyl compounds starting with alkenes by reaction with oxygen in the presence of the catalyst palladium chloride, PdCl2, supported by a little bit of copper chloride. So the catalyst is not PdCl2, but the catalyst is PdCl2. So that is actually the incorrect pair in the given list. And let us also see whether the other combinations are correct. Polythene preparation is a preparation of a polymer, TiCl4AlCH3 thrice. That is a well-known Ziegler-Natta catalyst. Ziegler-Natta polymerization of ethylene to polyethylene. So that is a correct option. The correct combination. And then you have the Haber process, the reaction between nitrogen and hydrogen to give ammonia. And we know that the catalyst used in the reaction is iron, finely divided iron catalyst or iron gauze catalyst you use. So iron is the catalyst, so that's a correct combination. And the last one is photography, AGBr. You know that in the classical photography, the photography plate or the photography film contains silver bromide emulsion. So the photosensitive material on the photographic film or photographic plate is silver bromide. So that also is correct combination. So the only incorrect combination is Wacker process PdCl2, and actually it must be Wacker process PdCl2. Moving to the next question, it is about the test for phenol. Phenolic group can be identified by, you are given 4 tests. One is a Thiolin dye test, carbylamine test, Lucas test, tolerance test. Suppose you move from the bottom to the top. Tolerance reagent, as you know, is used as a test for aldehydes and reducing sugars like glucose and fructose. So that is not the option. Lucas test, very famous, and all of you may be knowing, is a test to identify or to differentiate primary, secondary, and tertiary alcohol. So it is to differentiate primary, secondary, and tertiary alcohols. And the carbylamine test, as you know, is the test for primary amine. Primary amine, it's a reaction of a primary amine with a chloroform in the presence of alkali, and what is formed is the foul-smelling carbylamine, RNC, the isocyanide or carbylamine, which is extremely foul-smelling and can be easily identified, and that is a good test for primary amine. So carbylamine test for primary amine, Lucas test for differentiating primary, secondary, and tertiary alcohols, and tolerance test for detecting aldehydes and reducing agent. Reducing sugars. When you treat with a tolerance reagent, you get a bright metallic mirror, metallic silver mirror you get. Silver mirror test, it is also called. So B, C, and D are not the options. And of course, A must be the option. Thiolin dye test. And what is this Thiolin dye test? You must know. It's a test for phenol, where phenol is reacted upon by phthalic anhydride okay, in the presence of a drop of sulfuric acid. When phenol is reacted upon by phthalic anhydride, is formed the compound, the product formed is, okay, two molecules of phenol react like this. Okay. And the compound formed is what you call phenolphthalein. The compound very familiar to you, but actually it is an acid medium, and therefore the phenolphthalein form will not have any color. So to understand the color, you have to add some alkali to this after the reaction, or you pour the condense of the test tube in which you perform the reaction into alkali, sodium hydroxide solution, and phenolphthalein is pink in alkali, and therefore you can see a pink color. So this test is what you call the Thalin test for phenol. I repeat, phenol react with phthalic anhydride in the presence of sulfuric acid. You have the phenolphthalein formed. Being acid medium, it will not give any color. So to understand whether it is phenolphthalein or not, the contents of the test tube are poured into alkali solution when the phenolphthalein in alkaline medium gives a pink color, typical of phenolphthalein, and therefore you can confirm the compound phenol. So there is a very good test for phenol. So the answer of the question is A. A is the answer. Phenol can be identified by the Thalin test or phenolphthalein test. Okay. Now coming to the next question is a pretty fundamental thing. You have the habit of writing bond line representations. And in bond line representations, remember that it's just lines drawn. And this point, for example, in the structure drawn, represents a CH2 group. You don't show the carbon and you don't show the hydrogen in the bond line structure. Okay? The hydrocarbon residue, the hydrocarbon chain of the molecule is not shown by C and H. It is simply the lines drawn. And the meeting point represents the CH2 group between the lines, represents the CH2 group. You are seldom showing the hydrogen atoms. You are seldom showing the carbon. You don't write CH2 here. You don't write CH2 here. You don't write CH2 here in the bond line representation. So looking at the four structures, you will see that in the first structure, there is a hydrogen written on carbon. So it is not bond line structure. In the structure 2, of course, the other substituents are shown, the carbon, nitrogen, that is cyanide groups are shown, and the OH group is also shown. The functional groups are shown, or the substituents are shown, but at this point, you don't show carbon and hydrogen. That means it is the apt bond line structure of the compound with a C and H at this point. So B is a correct bond line representation. In C and D also you find on the carbon you have hydrogen atoms shown, and it is not customary to draw hydrogen atoms or carbon atoms in bond line structures. So C and D are also not bond line structures. The only correct bond line structure is B. B is the correct bond line structure. I hope it is followed. Coming to the next question, it's a statement type question. Okay? We have statement number 1. Oxygen being the first member of the group 16, oxygen, sulfur, selenium, tellurium, polonium, exhibits only -2 oxidation state. Is it correct? Oxygen, -2 oxidation state. Of course, in H2 it is -2. But what about the oxidation state of oxygen in H2O2? It is only -1. And what about the oxidation state of oxygen in OF2? It is +2. So oxygen has various oxidation states, -2, okay, -1, +2. So the first statement that oxygen has only -2 oxidation state is no longer valid. Therefore, the first statement is a wrong statement. Okay? the first statement is wrong. Now what about the second statement? Down the group 16, that is oxygen, sulfur, selenium, tellurium, polonium, okay, the plus 4 oxidation state decreases. Barring oxygen, you have 6 electrons in the outermost orbit for all the elements, sulfur, selenium, tellurium, polonium, and therefore it is an S2P4 configuration. And what you find is, as you go down the group, it's only these 4 electrons of the P4 are getting dislodged in forming the oxidation state of the element, whereas the S2 remains inert. And this effect is what is referred to as the inert pair effect. So the inert pair effect becomes dominant as you go down, which means the plus 4 oxidation state dominates, okay, and the plus 6 oxidation state, it is the tendency to acquire the plus 6 oxidation state is decreasing. So here the statement given is plus 4 oxidation state decreases and the plus 6 oxidation state increases. It must be the other way. The plus 6 oxidation state decreases and the plus 4 oxidation state increases, and therefore the reason is the inert pair effect. So the second statement is also wrong. So both statements are wrong. So both statements are wrong. Both statement 1 and 2 are incorrect, and therefore the correct option is B. B is the correct option. It's not a tough question, it's something very fundamental. And here is another question, and questions of this type are asked in almost all question papers, both in NEET and JEE. The cleavage of ethers using hydroiodic acid. And remember that this part of the ether is a tertiary butyl group. And a tertiary butyl group can be easily cleaved to form a tertiary carbocation, which is exceptionally stable, a tertiary carbocation, you know. So, naturally, the cleavage of this ether, okay, takes place like this only, HI. But this tertiary butyl group as tertiary butyl cation takes the I minus forming tertiary butyl iodide, and this part is the hydroxyl group, that is cyclohexanol. So the products are cyclohexanol and tertiary butyl iodide. So it is the option B, a question which has been asked so many times in various question papers, various examinations previously taken place. Such a question is every chance for you, at least 1 or 2 sessions of JEE getting questions of this type in the coming examination. Now question 12 is an incorrect statement regarding conformations of ethane. Which statements are incorrect? Now let us check the statements one by one. The conformations of ethane are interconvertible to one another. That's there. Interconversion is there because the interconversion requires only small energy. Energy difference is small, that the interconversions can take place. So the first statement is correct. Okay. The dihedral angle in the staggered conformation, this is the staggered conformation, and this angle is 60 degrees, that is also correct. Second statement is correct. The dihedral angle is 60 degrees. And the third, ethane has infinite number of conformations starting from the eclipsed. If you turn by 1 degree, you have one conformation. 2 degree, you have another conformation. 3 degree, you have a third conformation. So like that. So there are infinite number of conformations. So that is also a correct statement. And the fourth statement, the eclipsed conformation is the most stable conformation. Eclipsed conformation. How can the eclipsed conformation be most stable? There is repulsive interaction. The maximum repulsive interaction is there in the eclipsed conformation. Therefore, eclipsed conformation is the least stable conformation, isn't it? So the statement 4 is the incorrect statement. So the answer to this question is D, is the answer to the question. That is incorrect statement. The correct statement is the eclipsed conformation is the most stable conformation, or the staggered conformation is the most stable conformation, and the eclipsed conformation is the least stable conformation because of repulsive interactions between the eclipsed CH bonds. Coming to the next question, it is from the chapter on purification of organic compounds. The first chapter in organic chemistry, basic organic chemistry, you have one section, purification of organic compounds. There are the various methods discussed there, and one method is steam distillation. So for example, distillation of an essential oil from the leaves of a plant, or the separation of sandalwood oil from the bark of sandalwood, or even the separation of orthonitrophenol from a mixture of orthonitrophenol and paranitrophenol. Now these are possible by a method what you call steam distillation, where the component to be purified or separated is insoluble in water and is steam volatile. So the question is based on that. The technique used for purification steam volatile water immiscible compounds, steam volatile compounds and water immiscible compounds. The method is steam distillation. Other methods are not the methods. So the only correct option is D, it is steam distillation, used for the purification of steam volatile substances and water insoluble substances. Okay? And the next question, it is the simplest of the simplest questions in this particular question paper. Any student of chemistry will be able to answer it. The molecular formula of second homologue in the homologous series of monocarboxylic acids. Remember, the first number in the homologous series is formic acid. Don't forget that. It is formic acid. And the second compound is therefore acetic acid. That is the second homologue. And acetic acid has a molecular formula C2H4O2. Everybody knows. It is C2H4O2. So the correct option is D. D is the correct option. It is. And don't forget about formic acid. Whenever you spell out carboxylic acid, the name that always comes into your mind is acetic acid. So don't start counting the compounds starting from acetic acid. Remember that there is formic acid before acetic acid, and therefore acetic acid is the second homologue, and that's why the formula is C2H4O2. That's the correct answer. Okay. Now, choose the correct option having all the elements with the D10 electronic configuration. D10 configuration. Now, there are 4 options given. Suppose you start writing down the electronic configuration of all. I think it will take a lot of time. So how will you answer questions like this in minimum time possible? Of course, suppose you look at the first list. Your chromium there with atomic number 24, and it is 3D54S1. Immediately you have the configuration of chromium, because chromium is one case which we study where the half-filled d orbitals have exceptional stability. So when you see chromium 24, it is 3D54S1. So all the elements do not have the D10 configuration. Of course, Fe26 also, it is 3D6-4S2, and nickel is 3D8-4S2. So there, all of them do not have the D10 configuration. So that is not the correct option. In the second case also, there is chromium 24, 3D5-4S1. So the second list also cannot be the correct option. But now look at the third one, copper. With atomic number 29, it is 3D10-4S1. Okay? And zinc, it is atomic number 30, it is 3D10-4S2. Again, a D10 configuration. And cadmium, it is atomic number 48, zinc, cadmium, mercury. It is coming just below zinc. That means it will have the configuration 4010 5s2 for cadmium. The position of the elements in the periodic table must be clear to you. Often when students study the periodic classification of elements, they don't look at the periodic table. It is very important. In my humble opinion, as I said in another session, it is always good that you look into the periodic table at least for 5 minutes every day, so that you have a clear picture of what the periodic table is, what are the elements at particular positions, and what is the order of elements, what is the order of atomic numbers. Everything will be very clear to you. It will be in your mind. So when you find this element cadmium, remember that zinc, cadmium, and mercury, they are the 10th elements of the transition series 3D, 4D, 5D. So if zinc has a 3D10 configuration, of course, cadmium also has a 4D10 configuration, 4D10 5s2. Again, a D10 configuration. And coming to silver, that is with atomic number 47, atomic number silver 47, you must understand that it is nickel. What is the position of nickel in the periodic, position of silver in the periodic table? It is copper, silver, gold. Copper, silver, gold. Copper in the 3D series with a 3D10 4s1 configuration. Okay, 29 we have already written. And therefore, for the element just below copper, that is silver, the configuration is 4D10 5s1. So it is again a D10 configuration. So silver 47 has a D10 configuration. Cadmium 48 has a D10 configuration. Okay. And zinc 30 has a D10 configuration. And copper 29 also has a D10 configuration, which means all these four have D10 configuration. Now suppose you go on writing down the electronic configuration of all these, it will take a lot of time. Your precious time will be wasted. So there must be some other clue, some other simple method of answering such questions. And one method which I suggested is to take the configuration of at least one of them and see whether it is a D10. If not, forget about that. Then come to the next one. It's again chromium 24. It's a D5 configuration. So forget about it. And then come to C and check if it is 29 and 30. Copper 3D9 4s2, but it is 3D10 4s1 because exception stability for the D10 configuration. And zinc it is D10s2 configuration. And cadmium it is again D10s2 configuration. And silver it is D10s1 configuration. Okay, that means the third series is the correct. The third list is the correct list where all the elements given have D10 configuration. And the fourth one also, nickel 28 is 3D8, chromium 34. So if you focus your attention on chromium there, 3D5 4s1, 3D5 4s1, you can ignore possibilities A, B, and D. So the only possibility is C. You can immediately answer the question and get full credit for that. So that is some easy way of answering such questions. And I again tell you, you must have a clear-cut idea about the position of elements in the periodic table and the corresponding electronic configuration, the general electronic configuration you must know. And that is very important. It will help you in answering questions of this type in minimum time. So the method suggested is to look into the periodic table for 5 minutes every day. The periodic table will be in your mind. The whole periodic table will be in your mind. And no difficulty will be there for answering questions on periodic table and the electronic configuration of elements. The next question is again a statement type question. Statement 1 is in the lanthanides, for same as lanthanides, the formation C4+, cerium 4+ ion is favored by its noble gas configuration. Cerium has an atomic number 58. Okay, so when 4 electrons are lost, that cerium has 54 electrons, And these 54 electrons correspond to, again, if you have an idea about the periodic table, you will be immediately spelling out that 54 is the inert gas xenon. The inert gas, the noble gas is helium, atomic number 2, neon, atomic number 10, neon, argon, it is 18, krypton, it is 36, and xenon, it is 54. Okay? 2, 10, 18, 36, 54. So xenon has atomic number 54. So 54 represents a noble gas configuration. It is the xenon configuration, which is a configuration of cerium with 4 positive charges. Okay? So it has a noble gas configuration, and therefore it is exceedingly stable. Ce4 plus is very stable, and that is ceric ion. You have compounds like ceric sulfate, which are excellent oxidizing agents used in volumetric analysis for the standardization, estimation, etc. of reducing agents like Fe2 plus. So Ce4 plus is a pretty strong oxidizing agent, and during its function as an oxidizing agent, it is reduced to the +3 state, that is called the Ceres state. So ceric Ceres is a redox system. Ceric is the oxidizing agent and Ceres is the reducing agent. So the first statement is a pretty correct statement, first statement. Okay? The second statement is also a correct statement. Ce4 plus is favored by its noble gas configuration. That is very correct. And the second statement that Ce4 plus is a pretty strong oxidizing agent and is reduced to Ceres ion C3 plus, Ce4 plus, C3 plus represents a redox system. That's also a correct statement. So both the statements are correct. So both statement 1 and statement 2 are true. So B is the answer. The correct answer to this question is B. Right? Now coming to the next question, it is from organic chemistry. You are given certain conversions on the list 1 on the left, and you are given the corresponding reagents on the right. Of course, A is conversion of phenol to salicylic acid. Phenol to salicylic acid, you will be reminded of the reaction what is called the Kolb's reaction, where the reagent is alkali, carbon dioxide, and the salt formed is decomposed by acid HCl to give the product. So A is correlated to 4. Okay? Correlated to 4, that is the Kolb reaction. And the second is the conversion of B to salicylaldehyde. And that is a famous Riemann-Tiemann reaction, where you react with chloroform in the presence of alkali, okay, followed by acidification of the compound. So the second option, the second conversion, phenol to salicylaldehyde, can be correlated with option 3 on the right hand side. That is the Riemann-Tiemann reaction. Okay? Now, the third conversion is oxidation of phenol. It is oxidation to parabenzoquinone. And this takes place when phenol is oxidized by a comparatively strong oxidizing agent like potassium dichromate or sodium dichromate. So C can be correlated with 1. Okay? Oxidation reaction of phenol to parabenzoquinone. And the last one is D. D can be correlated to, it is formation of the compound anisole. That is methoxybenzene or anisole. It is very similar to a Williamson synthesis. But the only thing is that the phenol has to be converted into sodium salt, sodium phenoxide, by reaction with the NaOH. So you have the sodium phenoxide, and that on reaction with an alkyl halide like methyl chloride, you have the corresponding ether, and that is the Williamson synthesis. Williamson synthesis of ethers. So D can be correlated with 2. So I repeat, A is the Kolbe reaction and the reagents are as given in 4. B is the conversion of phenol to salicylaldehyde. It is a Riemann-Tiemann reaction and the reagents are as given in 3. And the third is the conversion of phenol to parabenzoquinone, the oxidizing agent sodium dichromate. So the reagent is 1. And the fourth one is phenol to anisole, and either by the Williamson synthesis by converting phenol into the sodium salt and reacting with the methyl chloride. So D is correlated, matching with 2. So A 4, B 3, C 1, and D 2 is the correct option, isn't it? That's the correct option. Okay. I already said the correct option. Now coming to the next question, it is again a pretty simple question. And there's a mistake in the question. It is NaBH4. It's not NaBH4. It is NaOH. It is NaOH. It should be NaOH. NaOH. In the second equation, the thing on the arrow mark is NaOH, sodium hydroxide. So now look at the question. It's a dihalogen compound, CH2 4 times Cl on either sides. Reaction with excessive ammonia. Excessive ammonia means the chlorine will be replaced by NH2. The chlorine will be replaced by NH2 on either sides. The chlorine will be replaced by NH2. And this NH2 will remain as NH3 plus Cl minus. CH2 4 times, and here also NH3 plus Cl minus. And when you treat this with alkali, NaOH, okay, the amine salt will be neutralized by the alkali to give back the free amine, that is NH2, CH2 4 times NH2. So simple a question. So the answer is C. It is tetramethylene diamine. That's a compound, tetramethylene diamine. So that is the product of the reaction. A pretty simple question. Now coming to the next question, it is something based on the SN1 mechanism, SN1 reactions. You study in connection with the nucleophilic substitution in the chapter haloalkanes and haloarenes. You have the detailed discussion of SN1 and SN2 reactions. And we know that SN1 reactions are most favored in the case of substrates which easily gives a stable carbocation. It's a carbocation mechanism in SN1 reaction. So look at these compounds and which of them are likely to undergo the SN1 reaction, which means which of them are likely to form a somewhat stable carbocation. The first one is, if you look at it, it is the allyl chloride. So it can give the allyl carbocation, which is stabilized by resonance, you know. Okay? So it follows SN1 mechanism. Carbocation is formed, which is stable. Okay? Now coming to the second one, if a carbocation is formed, that will be this carbocation. That's a vinylic type of carbocation. Vinyl is CH2 double bond CH plus. So this is methyl vinyl, in fact. Methyl vinyl type of carbocation. When the positive charge is on vinyl carbon, of course, it is not stabilized, and therefore it is very unlikely that it undergoes an SN1 mechanism. Now what about the third one? The third one is benzyl chloride and can form the benzyl carbocation, which again is stabilized by resonance. So possibility for SN1 reaction. And compound D is isopropyl chloride, a secondary alkyl halide, and we know that a secondary alkyl halide may undergo the reaction by SN1 mechanism or SN2 mechanism. So you cannot rule out SN1 mechanism for a secondary alkyl halide. It may take place by an SN1 mechanism or SN2 mechanism. So there is some chance for this compound to undergo reaction by SN1 mechanism. So SN1 is possible here also. So SN1 is possible in the first case, is possible in the third case, is possible in the fourth case, and SN1 is not possible in case B. So B is the answer. A question, a very standard question based on the things in the textbook. In the textbook, the NCERT textbook, these things are clearly illustrated while we discuss the stability of carbocations in the context of SN1 reactions. Okay, so we have already seen it is B only, that's the correct answer. So answer is C. Now coming to question number 20, which of the following statements is not correct about rusting of iron? It's a question from electrochemistry. Sometimes they ask questions on rusting of iron and what are the mechanisms by means of which the rusting of iron can be prevented. There are various methods, you know, and some statements about rusting of iron are given. In acidic oxides, the presence of acidic oxides in water, there is more rusting taking place because these acidic oxides will act as catalyst in the process of rusting. Of course, acid medium will enhance rusting. That's a correct statement. Coating of iron surface by tin. Of course, it's a method of preventing rusting. That is okay. But when the tin coating is removed, it is peeled off. The iron is exposed again to the atmosphere, and therefore the rusting will continue. So coating of iron surface by tin prevents rusting. That's the correct part of the statement. But even if the tin coating is peeling off, that is not correct. When the tin coating is peeled off, the iron is exposed to the atmosphere and therefore rusting will take place. Therefore, the second is not correct. Okay? According to the question, which of the following statements is not correct? Therefore, the second statement is not correct. And the third statement, when the pH lies above 9 or 10, of course, rusting of iron does not take place. Remember, rusting of iron is more favored in acidic pH. It's not favored in alkaline pH. When the pH is greater than 9, the rusting of iron doesn't take place. So only at lower pH, very close to 7 or less than 7 in acidic medium, the pH takes place. Beyond 9, the rusting doesn't take place. So that also is a correct statement. And the last statement, the rusting of iron, you know it's an electrochemical reaction, and therefore setting up of electrochemical cell on the surface of iron object. We have studied the mechanism of rusting, and it is an electrochemical reaction. So an electrochemical cell is actually set up at the surface of iron. You can interpret it like that. So that also is correct. So the only incorrect statement is statement B, and therefore B is the answer to the question. Okay? Now come the integer type questions. And this is a numerical calculation from thermodynamics. Okay? You are given the delta H0, and this is also the delta S0. That 0 is missing there. The standard entropy change. This is the standard enthalpy change. And you are asked to calculate the logarithm of the equilibrium constant. Of course, two relations are to be kept in mind to solve this question. One is the equation delta G0 is equal to delta H0 minus T delta S0. Okay, so by which you will be able to calculate delta G0. And the second equation is delta G0 is equal to minus 2.303 RT log GK, logarithm of K. Okay, so using the first statement, you calculate the value of delta G0 and post the value of delta G0 in the second equation, you solve for logarithm of constant. Okay, delta G0, of course, using the data, delta G0 is equal to delta H0, which is 77.2. It is given in kilojoules, convert into joules into 10 raised to 3 joule. Okay, minus T, temperature is 400 Kelvin, 400 into delta S0 is given as 122 joule. You calculate and get the answer. And I think you are likely to get the answer if you simplify it at 2400. So that is the value minus 28,400, 28,400 plus 28,400 joule, that is the result. And this 28,400 joule can now be equated to minus 2.303, okay, into 8.314, the value of R, into temperature again 400 into logarithm of K. So from this, you get the value of log K, and you will get the result. If you simplify, you can do it and get the value of log K as minus 3.708. So that's the value of log K, okay, minus 3.708. That's the value, and you are asked to fill up it as into 10 raised to minus 1. Into 10 raised to minus 1 means minus 37.08 into 10 raised to minus 1. Isn't it? So that will be the value. It is 37. You can neglect the 0.08. So the value is 37 minus 37 into 10 raised to minus 1. Okay? So that is that question. The next question. 1 mole, that 1 is missing there. 1 mole of lead sulfide, it is 1 mole. The question that 1 mole of lead sulfide is oxidized by X moles of ozone to get Y moles of O2. Now this is a simple reaction of ozone, and it is PbS plus O3 giving PbSO4, lead sulfate. You require 4 oxygen atoms, and therefore 4 moles of ozone plus 4 moles of oxygen on the right hand side. So 4 moles of ozone react with 1 mole of PbS. A very simple question on stoichiometry of this particular oxidation of lead sulfide by ozone to lead sulfate. PbS plus 4O3 giving PbSO4 plus 4O2. You have 4O3 and 4O2. So the number of moles of O3 is 4. The number of moles of O2 is also 4. So the total value X plus Y is 4 plus 4. That is 8. The answer is 8. Very simple. And coming to the next is an organic conversion. It is aniline. The question is about aniline. Okay. Is subjected to reaction with excess of acetic anhydride. Acetic anhydride. Acetic anhydride is CH3, CO twice O is acetic anhydride. To get the compound acetanilide, this is something that you study in the chapter on aniline. It is also studied in the practical chemistry of aniline. The preparation of acetanilide, that is there in the practical chemistry. So we have so many occasions of understanding this conversion, aniline to acetanilide. Acetanilide is NH, one hydrogen is replaced by an acetyl group. You know acetic anhydride is an acetylating agent. Acetylating agent means a hydrogen is replaced by acetyl group. So in this case, one hydrogen is replaced by a CH3CO group, and this compound is acetanilide. A simple stoichiometry based question. On this, you are taking 9.3 gram of aniline. So what is the molecular mass of aniline? You have to calculate the molecular mass of aniline. There are 6 carbon atoms. So 6 into 12, 72. You have 1, 2, 3, 4, 5 plus 2, 7 hydrogen atoms. Okay, and 14 is the atomic mass of nitrogen, making a total of 93 as a molecular mass of aniline. So 93 is the molecular mass of aniline. And what about the molecular mass of acetanilide if there is 100% completion as given in the question? So what is the molecular mass of acetanilide? One hydrogen. So out of 93, one hydrogen is lost. So you have 92 plus you have the acetyl group with the 2 carbon atoms, 24 plus 3 hydrogen atoms, 3 and 1 oxygen atom, 16. So what is the total? 92 plus 24, it is 116, isn't it? 116 plus 16, 132 plus 3, it will be 135. That's the molecular mass of acetanilide. The molecular mass is 135. Okay? The molecular mass is 135. So when 93 grams of aniline, that is 1 mole of aniline, is acetylated with acetic anhydride, the amount of acetanilide formed is 135, provided there is 100% completion of the reaction. And that is given in the problem. It is 100% completed. So from 93 gram, you are getting 135 gram. And therefore, from 9.3 gram, you will be getting 13.5 gram. Okay? 13.5 gram. But the result has to be expressed in dash into 10 raised to minus 1. So 10 raised to minus 1 means 135 into 10 raised to minus 1. Isn't it? So the result is 135. It has to be expressed as dash into 10 raised to minus 1. So the dash is 135. 135 into 10 raised to minus 1 is 13.5. Now such problems are simple. Organic conversions, but you have a stoichiometric sort of problem. Stoichiometric calculation. You have to calculate the molecular mass of the substrate, the molecular mass of the product. You apply the mole concept. 1 mole gives 1 mole of the product in this particular case. So molecular mass 93 and the molecular mass on the right is 135. So 93 grams give 135 grams. So 9.3 grams give 13.5 grams. And the 13.5 is expressed as 135 into 10 raised to minus 1. The problem is pretty simple, but you have to be a little bit careful while calculating the molecular mass. Don't forget to add all the atomic masses. Don't miss an atom while you calculate the molecular mass. And the next question is from inorganic chemistry, chemical bonding. Or you have come across a large number of polar molecules and a large number of non-polar molecules. The question is pretty simple, and you are asked to find out the number of non-polar molecules from this list. All very simple molecules. HF, obviously polar. It's a polar molecule. HF is polar. Water molecule has a dipole moment. The dipole moments are not getting cancelled. The dipole moments are reinforced, the bond moments are reinforced, and water molecule has polarity, it has a dipole moment, so water molecule is polar. Okay? And what about sulfur dioxide? Sulfur dioxide has an angular structure, and therefore the SO bonds have polarity, the dipole moments are not getting cancelled, and therefore there is polarity for sulfur dioxide, it is a polar molecule. But hydrogen molecule, is HEH. Of course, it is non-polar. Okay? And carbon dioxide, it is O double bond, C double bond O, a linear molecule. Again, the bond moments get cancelled in opposite directions. Therefore, carbon dioxide is a non-polar molecule. And methane, it's a symmetrical molecule, tetrahedral, symmetrical tetrahedral. And therefore, again, the bond moments get cancelled and the resultant dipole moment is 0. So, methane is a non-polar molecule. Okay? What about ammonia? Ammonia has a pyramidal structure, and that bond moments are not getting cancelled. Of course, partial cancellation is not at all there because the nitrogen is more electronegative. So, the bond moments are in this direction. Okay? And the lone pair moment in this direction. And therefore, for ammonia, there is a strong dipole moment. So it is a polar molecule. Ammonia is a polar molecule. What about HCl? H plus Cl minus or H delta plus Cl delta minus, polar molecule. Chloroform is a tetrahedral molecule. You have the 3 chlorine atoms like this, which have bond moments. The bond moments are not getting cancelled. Okay? And therefore, chloroform also is a polar molecule. Chloroform is polar molecule. And BF3, as you know, is a planar triangular molecule. A planar triangular molecule means the dipole moments get cancelled. It is symmetrical molecule. The resultant of the dipole moments of these 2 bonds will be cancelled by the dipole moment of BF bond. Bond moments get cancelled. I repeat, the resultant of these 2 bond moments will be cancelled by the bond moment BF, and therefore BF3 is also a non-polar molecule. So, what are the polar molecules? Hydrogen is a polar molecule. Okay. Carbon dioxide is a non-polar molecule. Hydrogen is non-polar. Carbon dioxide is non-polar. Methane is non-polar. And BF3 is non-polar. So, how many non-polar molecules out of the 4 non-polar molecules? Do you follow? You have 4 non-polar molecules. Okay. Now, there is a question from chemical kinetics. And this question has been asked many times as a multiple choice question. And this is something that is studied by heart by all students. I hope you are also very familiar with this. The time required for completion of 99.9% of a first order reaction is 10 times the half-life of the reaction. Now, if you don't know this statement, if this statement is not in your mind, how to do this problem? The time required for 99.9% completion. You take T 99.9 is equal to, your equation is this, K is equal to 2.303 by T. So naturally T is equal to 2.303 by K. Okay, log 99.9% completion. So suppose the initial amount is 100. Okay, the amount remaining is, it is 99.9% completed. So what remains is only 0.1. Okay, and what is the half-life of the reaction? T half. T half is 2.303 by K logarithm of 100 divided by 50. 50% reacts. So what remains is 50%. So what is the time required for 99.9% in relation to the half-life? If you take this ratio, T 99.9 divided by T half, that's equal to log 100 by 0.1. 100 by 0.1 is log 10 cubed divided by, isn't it? Log 2. And what is log 10 cubed? Log 10 cubed is equal to 3. And log 2 is 0.3010. Let us take it as 0.3. So 3 by 0.3 is 10. Now this is usually taught as a numerical question in the class. But students reading this question many times will have studied this thing as by heart, that the time required for completion of 99.9% of a first order reaction is 10 times the half-life. Okay, so if you know this statement, it is only a matter of fraction of a second to answer this question. And don't worry, if you do not remember the statement, you can do it from the first principles by using the first order rate equation. The time is equal to 2.303 by K log initial concentration by concentration at the time T. So for T 99.9 is equal to 2.303 by K log 100 by 0.1, and T half is equal to 2.303 by K log 100 by 50, and take the ratio of that, you will get it as 10. For the time required for 99.9% conversion is 10 times the half-life. Okay? Now, let us move on to the next question. Again, a pretty simple question. Only thing is that you have to concentrate on the structures of the compounds given and see whether it contains chiral carbon. A chiral carbon means a carbon whose valences are satisfied by 4 different atoms or groups. So try to locate the chiral carbon in these cases. The first compound, okay, here, this is a methyl group, and don't forget that there is a hydrogen atom here. So one will be a methyl group, second hydrogen, third a carbon, or a CH2 group here, or the remaining part of the, and here it is a carbonyl group. So for this carbon is a chiral carbon. Therefore it is a molecule containing chiral carbon. But in the next molecule, it's a CH2 group. Okay? Double bond O, double bond O. It's a CH2 group here. It's a CH2 group here. CH2 group here. None of the carbon atoms are chiral. So it's not a chiral molecule. In the third case, you find CH3, CH2, CHNO2, isn't it? CHNO2, COOH. So this carbon is chiral. It is linked to COOH, H, NO2, ethyl. Okay? So this is chiral. And then the compound CH3CH2, CHBr. Okay? CH2, CH3. Both are ethyl groups. So this carbon is not an asymmetric carbon, it is not chiral. Okay? Now the next compound CH3, CHI, CH2NO2. So CH2NO2 group here, a methyl group here, a hydrogen atom here, an iodine atom here. So this carbon is chiral. So this is chiral. And the fourth molecule, the fifth molecule there is, I will write here CH3, CH2, okay, CHOH, CHOH, CH2OH. So here is a CH2OH group, it's a CH3CH2 group, here a hydrogen atom and an OH group. That means this carbon is chiral. It's chiral carbon. And in the last molecule, it is CH3, CHI, okay, CHI, Ca2H5. This carbon is linked to 4 different groups, so it is chiral. So also this carbon is linked to 4 different groups. It is chiral, and they are dissimilar chiral carbon atoms, and therefore this molecule is optically active. The molecule is a chiral molecule. So how many are chiral molecules? 1, 2, 3, 4, and 5. Among the molecules given, you have 5 molecules containing chiral carbon atoms. 5 molecules. It's a very simple question because it is dealing with just the fundamentals, finding out chiral carbon in molecules or asymmetric carbon in molecules. A carbon in which the 4 valencies are satisfied by 4 different atoms or groups. So you can easily count the number of such carbon atoms and decide whether the molecule is chiral or not. Okay? Now coming to the next question. All these questions are pretty simple questions. Okay? Now here is a question on the hydrogen electrode. Hydrogen electrode, you know, for hydrogen electrode E equal to E0 cell or E0 electrode minus 2.303 RT by NF. It has been solved like this. So minus 2.303 RT by F is 0. So it is 0.059 by N. Suppose you take NS2 corresponding to the reaction. 2H plus 2 electron giving H2. Gas, and this is of a particular concentration, and the ratio in the Nernst equation will be logarithm of 1 by concentration of H plus square. Okay? And is your result for a hydrogen electrode, you know, is zero value. This is minus 0.059 by 2. And this will be logarithm of h plus to the power of minus 2. That is, log 1 is 0, 0 minus log h plus. Okay? H plus square. H plus square, that means the 2 will come here. And minus log h plus, you know, is pH. So this is equal to minus 0.059 by 2. Okay, minus log h plus is pH. So it will be 2 pH. 2 will get cancelled. So the value that you get is minus 0.059 pH. And the pH is given, it is 3. So it is minus 0.059 into 3. Okay, so the value that you get is 1, right? Minus 0.177, minus 0.177 volt will be the result. And you are asked to express it as dash into 10 raised to minus 2. So the dash is actually into 10 raised to minus 2. 10 raised to minus 2. So it will be 17.7 into 10 raised to minus 2. So that will be the value. And suppose you round off, you will get the value minus 18 into 10 raised to minus 2. So the result is 18. Actually, in the question, there I think is a minus value here. Minus dash into 10 raised to minus 2 volt. It will be 18. The result will be 18. It is 17.7. So you can put it as 18. Isn't it? Okay. It will be minus 18. That's very important. There will be a minus in the question here. Minus, okay, dash into 10 raised to minus 2. Then it is minus 18 into 10 raised to minus 2. So the value to be filled up here would be 18. If it were given as minus dash into 10 raised to minus 2. I think that was a question. And then is a question connected with molarity. Volume of 3 molar NaOH. 3 molar NaOH. Now what is the meaning of 3 molar NaOH? 3 mole in 1 liter. If 3 mole in 1 liter, it is 3 molar NaOH. Now the question is, the volume of 3 molar NaOH, which can be prepared from 84 gram of NaOH, is, that's a question. From 3 mole of NaOH dissolving in 1 liter, you get a 3 molar solution. 3 mole in 1 liter, it's a 3 molar solution. Now here it is 84 gram NaOH. 84 gram means 84 divided by the molecular mass of NaOH, 23 plus 16 plus 1, that is equal to 40. So what's the result? 84 by 40, it will be 2.1 mole. So if 3 mole in 1 liter, you have 3 molar. Okay? So if it is 2.1 mole, in how many liters will it be 3 molar? In 3 mole, in 1 liter, it is 3 molar. So if it is 0.3 mole in 1 liter, it will be 0.3 molar, isn't it? If it is 2.1 mole, okay, 2.1 mole, the amount given is only 2.1 mole. So 2.1 mole in how many liters will make it 3 molar? In how many liters will make it 3 molar? 3 mole in 1 liter makes it 3 molar. That means 2.1 mole in, it is 0.7 into 3 is 2.1. 0.7 into 3 is 2.1. So 3 mole in 1 liter, 3 molar. And therefore 2.1 mole in 0.7 liter. 2.1 by 7 is equal to 3. So 2.1 mole in 0.7 liter will make it 3 molar. So what's the question? Volume of 3 molar NaOH which can be prepared from 84 gram of NaOH is 0.7 liter. You can prepare 0.7 liter only, 0.7 liter because it's only 2.1 mole you have. So 3 molar solution can be prepared. The volume will be 0.7 liter and 1 liter is equal to, what is 1 liter? 1 liter is equal to 1 dm cube. 1 liter is the same as 1 dm cube. 1 liter is 1000 cm cube and 1000 cm cube is equal to 1 dm cube. So 1 liter is 1 dm cube. So 0.7 liter means 0.7 dm cube. 0.7 dm cube means 7 into 10 raised to minus 1 dm cube. So what is the answer? The answer is 7. 7 into 10 raised to minus 1 dm cube. So pretty simple problem with the concept of molarity in your mind. 3 mole in 1 liter, 3 molar. So if it is only 2.1 mole, what will be the volume for a 3 molar solution? It will be only 0.7 mole liter, and 0.7 liter you must know is same as 0.7 dm cube. 1 liter is 1 dm cube. So 0.7 dm cube and 0.7 is 7 into 10 raised to minus 1. So the answer to be filled up here is 7. The problems are simple, but you have to be a little bit careful about the units and also about the decimal points, etc. Then it is very easy to score marks by answering such questions. The questions, the numerical questions asked in JEE are not at all tough questions, but questions which can be answered in minimum time, but with maximum quotient. You have to be very careful about the units, careful about the decimal points, etc. Careful about the powers, careful about the negative powers, careful about the sign, whether it is plus or minus, etc. Now coming to the next question, the spin-only magnetic moment, question 29, the last but one question in this question paper. The spin-only magnetic moment value of square planar complex. It is given that it is a square planar complex. And with a platinum complex with a 4 coordination, of course there are 4 coordination here, 2 NH3, 1 chlorine, and CS3NH2. It's a 4 coordinated complex of platinum, which is given to be square planar, means the hybridization is dsp2 hybridization. The atomic number of platinum is 78. For this cation, okay, for this cation, the charge is +1. So there is already a Cl minus in the coordination sphere, the charge of which would have neutralized. So the platinum Pt is in the +2 oxidation state. In the +2 oxidation state with the dsp2 hybridization, +2 means the atomic number would be 78 for platinum. So it will have 76 electrons. So the D configuration, of course, for the what will be the D configuration for platinum? The D configuration for platinum will be, it is 5d8. So you have the 5 d orbitals, and you have the dsp2 hybridization, means 1 d orbital is being used for the hybridization, which means the remaining 8 electrons will be arranged in the the 4 d orbitals like this, with all the electrons paired, which means no unpaired electron is there in this complex. If there is no unpaired electron, what will be the spin-only magnetic moment? The spin-only magnetic moment will be 0, because there is no unpaired electron in this complex. A good question, but a very simple question. You must know that it is dsp2 hybridization, one thing, and the d electrons in platinum 2+, it is 8, and therefore all the d electrons will be in the paired state in the 4 d orbitals. So no unpaired electron in this Pt2+ complex, and therefore the magnetic moment, the spin-only magnetic moment is 0. Okay? And here again, it's an electronic configuration based question. I told you earlier that you must have an idea about the periodic table, the position of the elements in the periodic table. Okay? Now the question is regarding how many of them have noble gas configuration. Now what do you mean by a noble gas configuration? The NS2NP6 configuration in the outermost shell. This is the noble gas configuration. So how many of these ions have the NS2NP6 configuration in the outermost shell? That's a question. And certain values, it's very easy to remember these values. For strontium 2+, strontium atomic number is 38, and we know that strontium is a second group element. So when strontium loses those 2 electrons, obviously the number of electrons will be same as the number of electrons in the preceding inert gas. So Sr2+ has an inert gas configuration NS2NP6. Of course, it will have 36 electrons, and 36 electrons means, as I told you earlier, helium has 2 electrons, neon has 10 electrons, then argon has 18 electrons, krypton has 36 electrons, and xenon has 54 electrons. Okay? So you have the 36 electrons in Sr2+. That means it has a helium, neon, argon. Okay? Helium, neon, argon, krypton, and xenon. So it has a krypton configuration with the 36 electrons. So it is an NS2NP2 configuration. You need not write the electronic configuration as such. You can find which of them has the NS2NP6 configuration by thinking like this. Now, so is the case with the cesium plus, CS plus, atomic number is 55. It is given, and you know that it's an element in the first group of the periodic table. So when 1 electron is lost from it, it will have 54 electrons, and the 54 electron is same as the 54 electrons in the inert gas. So the atomic number 54, helium, neon, argon, krypton, xenon. Okay? So 54 electrons in CS plus is similar to a xenon configuration. That means it also is NS2NP6 configuration. Lanthanum 2+, 57 atomic number, and we know that it is the first element in the third transition series, but beyond that you have the lanthanide series of elements. So actually 57, if it loses 2 electrons, then it again will have just 1 electron there. So 57 minus 2 will be 55, and 55 is the atomic number of cesium, and it belongs to the first group. Okay, so it has as many electrons as CS plus 55. So it is not. If it is 54, it is an inert gas configuration. It is 55 when lanthanum loses 2 electrons. So it is not an inert gas configuration. It is not a noble gas configuration. And so is the case with the Pb2+. It is 82. When it loses 2 electrons, it is 80. It's nowhere near a noble gas configuration. But in the case of ytterbium, the atomic number is 70. The atomic number is 70. And ytterbium, I hope you know, is the element just before lutetium in the lanthanide series of elements. Again, I told you, try to have in your mind the position of the element in the periodic table. At least certain elements in the periodic table, lutetium is the last element in the lanthanide series. Just before that is the element ytterbium. And ytterbium has atomic number 70. Ytterbium has atomic number 70 means it has the 4f14. 4f14. Okay, 4f14. Okay, it is 4f14, 5s2, 5p6, 6s2 configuration. And when it loses these 2 electrons from the 6 orbital, which is the outermost shell, in the ion formed Yb2 plus, remember that in the 5th shell you have 5s2, 5p2. So this happens to be the outermost shell for Yb2 plus, which has the ns2 np6 configuration. Therefore, Yb2 plus has ns2 np6 configuration in the outermost shell. Remember that ytterbium as such has only 2 electrons in the outermost shell, 6s2 configuration. So when those 2 electrons are dislodged from the ytterbium atom, the ytterbium 2 plus ion contains the s2p6 configuration, the penultimate shell, which now happens to be the outermost shell of the ion. I hope you understand the point. The outermost shell of the ion is the 5th shell, and the 5th shell contains the 5s2, 5p6 configuration, and that is ns2, np6 configuration. And therefore, Yb2 plus has a noble gas configuration in the outermost shell, right? And Fe2 plus, of course, it is 3d6 4s2. When the 4s2 electrons are lost, it is 3d6 configuration. It is nowhere near the noble gas configuration. So the noble gas configuration is there for Sr2 plus with the 36 electrons in the ion, Cs plus with the 54 electrons in the ion, similar to xenon. And for ytterbium 2 plus, remember it's a lanthanide element, the outermost configuration 6s2. When those 2 electrons are lost to form the ytterbium 2 plus ion, the previous shell now contains the 5s2, 5p6 configuration, and this shell now happens to be the outermost shell for the ion. And therefore, for the ion, the outermost shell configuration is 5s2, 5p6. It is ns2, np6, and therefore it also is a noble gas configuration. Correct? And therefore, the answer to this question is 3. There are 3 ions which are having noble gas configuration in the outermost shell. The number of ions with the noble gas configuration in the outermost shell. It is Sr2 plus, it is Cs plus, and Yb2 plus. Okay? So answering such questions, it is very important that students have a right impression, right understanding about the position of elements in the periodic table. Otherwise, writing down the electronic configuration of all this, starting with the 1s2, 2s2, 2 pieces like that, it will take half an hour or so. So it will be very difficult for you to, but knowing the position of the element in the periodic table and also the element next to it or before it in the periodic table, or to what group or to what period or to what row this particular element belongs, you will be able to write down the correct answers to questions like this. So I once again tell you, there are so many questions in periodic table asked in this particular question paper, mainly based on the electronic configurations, and you will be able to answer such questions pretty easily, provided you have the right knowledge about the groups, the periods, the position of elements in the periodic table, and so on. Okay? So that's the last question. I think we have discussed the questions, most of the questions in good detail, so that you get a clear understanding of what the question is, how to answer the question, how to answer the question in the minimum time. That's important. How to answer the question most easily in the minimum time. Time management is very important in answering questions in a question paper. So with these words, I conclude. Wish you all the very best, and I sign out.